Privilege to introduce Professor Siris sir. So, Dr. Siris Sonawane is a distinguished professor in the Department of Chemical Engineering at the National Institute of Technology, Warangal, and currently serves as the Dean for Research and Development, and widely recognized for his profile research output. Dr. Sonawane is the Institute's most published and cited academician, with over 230 publications in leading national and international peer journals, and he has also made significant contributions to the field through his editorial work on 8 books and over 60 book chapters. So his research interest encompasses a diverse range of areas, including process intensification, nanomaterials, fuel cells, and wastewater treatment. And Dr. Sonawane has secured significant funding through prestigious projects from agencies and schemes such as Imprint, Spark, Water Treatment Initiative, ISRO, DRDO, MITI, MOEF, DBD, and DST, and has undertaken collaborative research endeavor with international partners in Russia, Tunisia, and Singapore. He has also actively engaged in industrial collaborations, providing consultancy services for over 25 industrial projects. And recognizing his exceptional contribution, Dr. Siris has been appointed as a chair professor for Chiron Life Sciences Private Limited, Ahmedabad. He is a recipient of numerous prestigious fellowships, including Boy Scouts, Erasmus Mundus, and Humboldt, NAVA, and IGSTC Connect Plus, so on. So he accolades further includes prestigious awards such as Hindustan Door Oliver Award from the Indian Institute of Chemical Engineer for excellence in the application of science and technology for rural development, the Vasvik Award for outstanding contribution in industrial chemical engineering research, and Best Faculty and Research Award from NIT Warangal. Dr. Sonawane is an active member of various research and academic societies and has served as a guest editor for several leading journals. So on this occasion, I extend my sincere congratulations to Professor Sonawane and his recent appointment to the General Body of Wetland International South Asia Society. And with these words, I welcome Mr. Dr. Professor Siris Sonawane sir to deliver his lecture. Yes, sir.
So I would like to invite Professor Pankaj to give a memento to Professor.
Produce, once we have set the parameters, we will have the continuous same quality. Okay? So let us look to that how we can do it. So other things I will just skip it. Okay? I will just see that basically these methodologies, micro-reactor based one, we can produce. I mean to say the manufacturing facility will be in a very small room. Okay? I will show some Corning reactor also. They are very small. and you can produce in a very small room all this some per month per tonnage we can produce. There is very important advantage that using this methodology we are getting the products per unit manufacturing is very higher, capacity you are increasing, okay, and there is also high yield and selectivity. So one of my student, that whatever the student I work, other things are definition wise if you see, this is what I want to say. So bigger plants are there manufacturing, even if you talked about this nanoparticle, I will give you one example of conductive adhesive. Recently, I mean on the 10th, I invite you all the people for this technology transfer also. Okay, there is one of my student who has produced the nanowires, and you will get the exposure also today. If you are going to be there in the chemical department during the experimental session, you attend that. So there is a nanowires production, and is going to be used it for the adhesive and epoxy resin. So basically, if you see, our plant sizes are quite bigger, but we can have in very small size plant this production it happens. So all these are related to chemical. So 2002 we have this one, by 2025 we will have very smaller space. Why it is? Because as a bigger size the hazards are very typical. You can see the Bhopal gas tragedy, all of us know, plant size is larger, methyl isocyanate gas has been liberated, and based on that it has happened. Now this is conventional method, we usually do it scaling up. You can see in the R&D you have this lab, then you have on the pilot scale, again goes to the what it's called the plant manufacturing, correct? So in place of that, on the single plate, for example fuel cell, the stack it is, you also get on a single cell also. So you can first make it on the single plate. So let us say it is in a micro-reactor, and then you can number up it. So it is very simple. Once you produce into the number of one plate, the same will be on the product onto the number of plates. So it is in a mass production. I will show you the actual scale in that also, okay. So this is basically the methodology. There are number of reactors are there. For example, micro-reactor. So this is one. Capillary if you take, for example, if you see on the back side of a fridge, there are capillaries are there. Different capillaries you will find, okay. So capillary, what is the advantage you are getting? Basically the surface area is quite higher. Because of that you have the better mass and heat transport, okay. So basically the flow will be in the laminar, and maybe Reynolds number is maybe less than 500, but the layer distance is quite smaller. Because of that you have the better mixing. If doesn't mixing happens, you have the junctions are there, Y junction and T junctions. Based on the junctions you can have the mixing and goes to the one to the other ton, and then you have this one. So this is the way for the nanoparticles also we can able to produce that, okay. So let us see how it has been done. So we will go to the micro-reactor. So as I told you, it is the dimensions between the maybe 0.1 to 1000, okay. There is also, it is could be on the flat plate also, you have done grooving is been carried out, and from there the material is been produced, okay. So similar fashion we will produce the using for the nanomaterials specifically for fuel cell. In the fuel cell there is one catalyst is been used, because there is an anode and cathode, it is been coated, okay. It is a specific catalyst called as a platinum, okay. Platinum is gives you the both the reactions, reduction and oxidation reaction, okay. It is very unique catalyst, noble catalyst. It won't give the much poisoning. In the carbon black, it has been added in the nano size, okay. Why it is in nano size to be added? Because surface area will be higher, quantity required will be the lesser. So per meter square loading will be, you are bringing down lower, okay. So this is what the advantage, because platinum if you look, it is very costly, costlier than the your maybe gold, okay, very costly material. So precursor are costly and the platinum cost is high. So if you produced in the nano size with a uniform particle size distribution, narrow size distribution, it is the advantage, okay. Now if you produce this particle using the batch reactor, you will have the particle very wider distribution. Maybe wider distribution means some particle will be of, let's say 100 nanometer, some will be 2000 nanometer, 200 nanometer, some will be in the micron size, okay, sub-micron size, and you will have the distribution with the very wider. So because of that, overall performance is going to be reduced. So if I have the range of, narrow range of a particle, I will have the specific surface area, and based on that I will have the better advantage, okay. So these are the basic requirements are there, micro-reactor. So we can produce this one in the micro-reactor, okay. So basically if we look to this micro-reactor significance, it is as a scaling up means small reactor, you will take the reaction in the small what is called flask, go to the bigger size 1 liter and then begins in the bigger kettle. So in place of that, it is very simple, you have the number of plates only, just need to increase, okay. You have the playing cards, you can see, you have the playing cards together and one playing cards, right. So all these playing cards is kind of, you can say it is the kind of total what is called numbers, you are making it together, okay. Stacking, we can say, stack, okay. So let us look to reactor. This is a kind of micro reactor, you can see, this is a matchbox, they are very smaller in size, okay. So you can see the, what is called the number of channels, they could be, 1 mm, 2 mm channels are there, okay. Through the channel, the reaction has been happening, okay. So this is one type, okay, stainless steel, I will show you, you can have also your reactor also. This is channel type, you can see it is an acrylic, what is called micro reactor. It is an acrylic, inlets are there and then the reaction goes and flows through it and then outlet it will come, okay. So this is one. Capillary I will show you, glass, silicon or others are there, you can see here, okay. Mixing will come and happens, or maybe two will be mixed and then it will come down and then mix and then product is going to be out, okay. So from Hyderabad, there is one company, it is called micro-reactor, Chem India. They have this reactor, you can see it. This is also mechanical engineering, you can design this one. Plates you can make it, grooving you can do it, okay. On the graphite you can have, like bipolar plates of a fuel cell, you can see here. So basically the structure is very important. Why it is important? Because it will give you the, the mixing as well as the, residence time required, okay. So here you see, this is T junction. Let's say if you have 3 components, you can add 1, 2, 3, or 2 components you can add 1, 2, mix it, goes here. What is happening here? Splitting. Again mixing, then curve. So number of turns will be there, you have the again mixing, okay. Residence time you are getting more, okay. So like that, it will have the mixing and then it has comes and goes out. I will show you. So platinum catalyst we have produced through this kind of methodology, through this stainless steel, okay. So there is also other techniques are there for fabrication, it is called ligab techniques and other micro machining. Today you are going to see one more reactor, okay. Why I am showing this? Because for there is earlier methodologies, you don't need to go to the chemist or chemical engineer, you can also, we can do it ourselves, reactor manufacturing, as well as you can also produce it yourself. You know the mobile glass, what is the mobile glass name is? On the top you have the mobile glass is there, right? It is called Gorilla Glass. Who is the manufacturer? Gorilla, Corning, okay.
Corning technology. Gorilla is a brand name up there, right? The Corning technologies. Corning is in the optical fibers, and that Corning has produced also in this reactor. Okay, that is called as an that is called a reactor. What is called as an advanced flow reactor. Okay, I will show you how it is useful to produce this nanoparticle production. Okay, iron oxide, then cobalt, nickel, number of other nanoparticles we usually produce. I will show you how it is been useful. Now, why we should go with this kind of reactors? Okay, I have shown you there is your one structure of that Chem India. What is the structure? Just see, coming, mixing, splitting, mixing, and then again splitting, and then goes like this, right? Again splitting, mixing at separate place, right? This is one configuration. Corning has done the research with one of the professor in the USA, okay, in the MIT, with I forgot the name of that professor, with the professor Hijar or somebody, I forgot. So in that one, initially they come up with one reactor configuration. Okay, that reactor configuration we will see how it is. Okay, then we will come back. Why I am showing this? Because to make the nanoparticles, these things are very important. Mixing, one parameter. Residence time, second parameter. Why? Particle initiation, nucleation and growth, it will happen. Particle will have the agglomeration. Once it is agglomeration or the unified distribution, these are the major challenges. Practically I will show you how it has been impacting. Okay, I can show you some videos also about Corning, then we can come back, that is also fine. Okay, we will see video and then we will come back so that you can understand. Can you see this? Sorry, I mean, I am not getting the video. I mean, audio is not there. Ek minute. Otherwise, I have this one. Speakers are there. Yeah.
Is it playing?
Yeah, it's playing. It's playing. Okay, leave it. We will see. I will show you. Can you see this one?
Speaker is working.
Speaker is working, but because of this attachment, the speaker will also not work. That's what the issue is. I will show you later. Okay, can you see this one? What this structure is? This is all glass plates attached. You can see this heart shaped structure is there. These are the hearts are there. Okay, and these hearts are connected with the other heart. Okay. Why it is? There will be a mixture, two reactants are coming. For example, let us talk. You want to make a platinum nanoparticles. How you will make? It is required, for example, a fuel cell. How you will make platinum? Chloroplatinic acid you will take, precursor. Okay? And then you will add the sodium borohydride, one reducing agent. A plus B gives you C, simple reaction. So A and B you are adding it, but just adding is not sufficient. It will precipitate out the particle of a platinum. So it should have the proper mixing, okay, and then go to that. So here if you see, goes to the second, third end like this, mixing takes place, goes like this, and mixing happens and then comes out. Okay. So like this is one plate. Okay. Like this you can see that there are number of plates are there. Okay. I will show you. This is the configuration, for example. Okay. Additional through the pumps you are passing through it. Okay. Here you can see these are the flow, and then reaction it happens and so fast, and then you are getting output. Now whatever other things you are seeing like this round shapes, this one is for the cooling, or maybe if you require a heating you can use that for heating. So this is one plate. You can have the number of plates also. This is one plate I talked. Okay, you can have the other plates also. So you can have this mixing. Okay, so you can have this one plate, two plates. Okay, so other things are there. So okay. Okay. So this is what we have this reactor. Others are also you can have. Okay. Some of the, this is the, for your lab, if you don't have, you can use a syringe pump. Doctors use a syringe pump to, pass the liquid, right? So same way you can have this syringe pumps. Okay. Attach that syringe pump with this single plate, number of, frames. This is only 1, 2, 3, 4 kind of. Now someone say that I required 10 tons per month. The reactor size is different. They are of this 2 feet or 3 feet size reactor plates are there, and then number of plates will be more. In the same hall you can produce that material. Okay. So this is how it is. Now there are also other capillaries. I told you that could be of a glass also. You can see these configurations in my lab. So you can have these reactions and it is going to be happen. Okay. There is also, as I told you, that capillaries, if you look for the refrigeration shop, you will get varieties of capillaries. Okay. From 2 mm, 3 mm, different junctions you can create. Only limitation, it is made up of a copper. You can also have your from the steel. Okay. We can have this one using the other possibilities through here, and you can syringe and pump it. Okay. So I don't want to go in the detail. Now you look, this is steel capillary through which again syringe pump you can produce. There is also possibility that simple Teflon tubes also you can use it. Okay, to produce these nanoparticles. As I told you, this is heart-shaped structure for your corning. This is the Teflon helical. Number of coils are important. The number varies. Mixing will be there. Number of tons will going to impact onto the overall product. Okay. So you can use the number of cases. I don't want to go in this detail about what it is called biodiesel and other peracetic acid chemical production. We don't want to go. Let us go to the nanoparticle. You have already learned. It is for the top-down approach and bottom-up approach. This is bottom-up approach, and using this one, we can use the micro-reaction. So copper spiral wires, you can use it to produce this particle. You can see the distribution. Distribution is very narrow. You can see here 6 to 18 nanometer size, very smaller in size of iron oxide. Okay. Same using the Corning and AFR reactor. Okay. So space-time, their flow rate, space-time, it is reactor size divided by the flow rate. Okay, V upon volumetric flow rate, volume of a reactor divided by the volumetric flow rate. Okay, that space-time will be defined, will be have the two impacts. One is how much flow rate is there and what is the volume of reactor. So that will impact onto your particle size. Okay, residence time. So this is again, you can have other zinc oxide nanoparticles. You can see here earlier the sizes are, PhDs are important. As I told you, it should be narrow. Okay, and with AFR and reactor configuration also plays very important role to produce this nanoparticle. Okay. So there is also one possibility about a nickel. One of the master student, she started working on that. You can try to see the CFD configurations. I think in your department, the Professor Karthik and other people are working on that micro-reactors, micro channels actually, not micro reactors, but channels, same thing it is. Okay. So basically this nickel particle to replace the platinum, this we can also produce using the micro reactor. Okay. So as I discussed with you, these are the major important things what I want to talk to you. Okay. Platinum and palladium catalyst. Okay. As I told you, these are the very important used into the fuel cell, anode and cathode along with the carbon. It is called XC75, some specific grade is there. Okay. That contains the platinum catalyst, commercial grade. We can also produce this one. So our motive intention was, can we reduce that quantity of platinum? Can we continuously produce that platinum? Or can we use that precursor, what is called liquor, whatever it is formed, directly you can add into the carbon and then make it the your membrane electrode assembly for required for the fuel cell. So this is the Y junctions, and then nanoparticle formations is taking place. Okay. So simple capillary you can use is for the micro reactor. So you can see here, these are very, scale is 100 nanometer. Okay. So the size is quite smaller. Okay. You can look here, 50 nanometers size. So how much smaller? Maybe in a range of 10 to 15 nanometer size. Okay. So the optimization is again made, and then with minimum quantity required you can produce. Okay. So these are with different solvents and with water. Differences you can look. Particles are completely separated. There is no much agglomeration. Smaller in size, very uniform size. Distribution. Mono disperse is always required, desired, same size. Okay. Is always desired, but it is not possible to come. Very few, like an ultrasound cavitation only can give you this one. But this is how we can reach to the narrow distribution. Okay. So for that, using this one, we can have the graphene and palladium and other catalysts. You can coat it and then you can make this sizes. Okay. These XRDs I don't want to go. You can see palladium is also same thing. What is the impact? You can see there are different flow concentrations, flow rate, average size. What is the impact of maybe your NaBH4 addition or this PD4 addition will have the impact onto your overall sizes. Okay. So can have this different configurations, you can reducing agents, you can use it different, citric acid or maybe ascorbic, and then you can have. In India, there are a number of other configurations have been produced. One of the companies there, it is called Amar Equipments. Okay. So they with a National Chemical Laboratory Pune, they developed this reactor. You can see their own configuration is different. Okay. You can see here, this is spiral. Okay. Then goes to the mixing and splitting, then again spiral and then outlet. Okay. So it becomes their own configuration. You can have this your own design of a micro reactor. Okay. One of the student from NIT Warangal, MTech student, he worked with a Corning initially, then he has started his own company. It was earlier incubated in NIT Warangal. Okay. He is also having his own configuration. Florex is name of the company, I will show you. Okay. Now how they make it commercialize, I will show you the actual plant size of the for the reactors in the China, okay. But don't think about the China, we can have our own configurations here also. The example is, it is scalable, that what I want to show you, okay. So now let us look to some of the other configurations. So CFD studies also, one of a student did it, and you can see that how the mixing is important. For nanoparticle, as I told you, this mixing and concentrations, they are playing major role, okay. So get the mixing, configurations are important, okay. So if you have this, what it is called, back pressure zones creations is very important, and this, turns are important. So you will create and then mix it, or maybe coming mix it like this, okay. So initially you can see here with a different residence time, the mixing and the concentration zones will going to change. You can see here the configuration within a different CFD studies there, okay. So let us not to go in this detail, because we are not, but this one is the interesting slide, okay. I will just show you one commercial finals, one slide, then you can understand. You can see it, whatever you are going to see the reactor in our lab, it is this low flow reactor of a Corning, okay, very small. How much it is here? 5 tons per year, very small. Number of plates are more. You can produce 2000 ton per year. How much the reactor size? You can see 2 feet, 3 feet, okay. It is of a G4. So we have low flow reactor, so you can have the scalability is there, okay. Continuously you can produce this one, okay, this material. So this is important for this continuous manufacturing, okay. I have given this example of fuel cell. Let us see how this other student did it, and then we will go to, we'll go to the Prashant slide. Even we can go to the Rajesh slide also later. So that Prashant has did with this platinum production and with a number of other cobalt and other things. You can see here, this Vulcan XC is the grade, commercial grade of used for the carbon support. Vulcan XC 72, okay. I might have told 76 or 74, okay. In that one, in place of that, we can use this RGO, but this platinum or maybe nickel or molybdate, we can replace this platinum catalyst, because it is a costlier, so non-noble metals you can replace to use it, this catalyst, okay. Same way, so we can produce it into the this what is called in the micro-reactor, okay. Now these are some of the performances are there once we use that catalyst onto the in the anode and cathode. So you can see here, platinum and molybdate both are there. They have been utilized to produce this one, as well as you can see here, there is also 40% replacement is there. Here you can see, these are the platinum catalyst prepared using the micro-reactor. You can see these are the two important areas are there. What it is called, based on that adsorption and desorption area, it is a cyclic voltammetry graph, no need to go in the detail, but active surface area is improved using this continuous manufacturing, okay. That is what the intention is. Here is also you can see platinum, this nickel is somewhat replaced, so electrochemical surface area you can see here 26, 14, earlier it was 7 to 6 to 7, which have been largely been improved, okay, this area, okay. So this is one of the advantage when you make this continuous manufacturing, okay. Now I will show you the one of the study of the student have did it actually. Okay, there is also polymer nanoparticles you can produce for polyaniline using the microreactor, but it is not of your interest. Okay, so it is related to energy applications, you can do it. Okay, so let us look to the other possibility of the corning. We will go to the so maybe if you are coming, this is one of the possibility. Let us look to the application first, and then we will go to the problem. First look to the problem. See, conductive adhesives generally been used in the flexible electronics. RID is there, there is also it has been utilized. Ink are there, for example, conductive ink is been coated so that you will get an flowing the current through this area. Or maybe if you want to have connect the some two components, then you will have this adhesive. So adhesive will contain two components. One is the silver particle and one is the epoxy resin. Epoxy resin gives you the adhesion and silver particle will give the conductance. But problem is that the silver quantity, if you look, it is almost 80% addition and 20% is epoxy. Okay? So these particles of silver, they are the flakes and they are in the micron size particle. So understanding is that can we have the silver nano wires, okay, so that you will have the conductivity, quantity required will be the also lesser, surface area will be there higher, and overall performance will going to be improved. And this is what the current trend goes on in the conductive ink industry as well as into adhesive industry. But the problem is that we should have the continuous manufacturing. It should not, whatever you have added, once you find the nanowires, tomorrow I will get the silver particles only, round sphere. So it should not happen. So that's what I am saying, that continuous manufacturing has this advantage. You will have the continuous nanowire production. Okay. So let us look how it is been made. So this is, for example, we made within two atoms basically. Okay. For example, you look to the capillary, through stock solution pass through the syringe pump, and there are some of the chemicals and other things are there. You can look to the residence time and reactor, and then you can produce these wires. You can see here some of the residence time, as I told you, they are also very important. Initially you see in the 5 minutes residence time, let's say flow rate is slower, maybe whatever it is given 10 ml per minute, for example, okay, lesser than that. Reactor size is 1 meter. Then you will initially find there is almost a spherical particles only. You increase the residence time, somewhat you can see the length has been increasing. It is not easy to make this optimization. You may be thinking that it is very easy, just add and get it like that. But if you see, it took longer time to optimize this thing. Okay, and then you can have this latter wire generations. You can see here, these are the again temperature optimizations of the reactor. You can see the wire. You can see more detail in the wires here. You can see here these are particles. At what temperature, if you look to this one, you are getting this one. But if you increase one, okay, higher, lower this copper chloride concentration, you will find almost uniform wires, no particle. So once reactor size, capillary length, flow rate, concentration, once it is fixed, I am getting the continuous wire productions only. Okay? So this methodology, as I am telling you, that is been produced, and this it is the student has been going to be PhD student only. Okay? He did it, and he made it own startup now, and he is going to use these nanowires for the adhesive and conductive ink. Okay? So you can see here, these are the optimized length of a nanowires is important. So it will have the better conductance directly, and these are the some of the optimized results are there, no need to go. Now how to scale up it? Scale up will be very easy, as I told you. You want to have more tonnage, I will have the capillary, the different capillaries, and you can have this one continuously you can produce, and the capillary coils will be different, capacity we can able to produce. It is very slow written here, but actually we can produce in the large quantity. Okay? So in this way, this is somewhat in a conductive ink formulations. You need to be measured in terms of resistance actually. Okay? And this is the ink formulation which contains, you can look to here, almost 70% you can use it. Okay? And maybe 30% nanowires also we can able to width and lengthwise specifications. Okay. So this is what the actual ink shelf life you can have for longer time, maybe it is giving, these are all the nanowires only, and you have this shelf life, bulk resistance is not much change, it has 10 to 12. Okay. I can show you, this is the, you can see here, screen printed, screen printing is been used, you can see the screen printing also in the lab. Okay. And how it has been here, you can see this is very small gap, and from there you can see that conductance also, okay, of this nanowire. Okay. So our responsibility is to be make it at a large scale, as I told you again, to make it in a ink at homogenizers and other things are there. You can see the bulk prepared ink also in the lab. Okay. So this is one story. So now I will tell you another thing about what you are going to see, another thing in the lab. Okay. You know the atomization process. Okay. Atomization process, for example, in the engine, IC engine, you have the atomized fuel, you are putting it in the engine. What is the specialty? You are making it smaller droplet. Okay. In nanotechnology also, this droplet size has very much impact on to the structures. Okay. This is very important. So we will see, you will also going to see that atomization process, you can use an ultrasound atomization, you will get in a finer droplet. Finer droplet will have the impact onto structures. Let's see that how it is impact, and this is very useful. Okay. So again, we can say not nanowires, but you can say the rods. Okay. They are in bigger in shapes, structure. Okay. You can see here, basically ultrasound are the waves which are about 20 kilohertz, and dogs and bats can only hear this ultrasound waves. Okay. We human being cannot hear that waves. But the interesting thing about this ultrasound, you can make the vibration and you can make the droplets smaller in size. Other chemical effect I will tell you later, but you can look normal atomization and ultrasound atomization. Ultrasound atomization will have the finer in size. So look to the application. For example, I required nano rods, and if I want to prepare it, there is only a sealer method, usually a deposition method it takes, and this deposition is not guaranteed that how whether it will have the nanowires or the particle, because in the formation there is initiation, nucleation and formation, three stages are there, and the particle growth will depends on this mechanism. So to be have, let us look to that how it is been made. Okay. So basically you see the liquid has been passed through this ultrasound generator, and here it is basically liquid. Once it is, there is a small orifice here. Okay. Once the liquid comes into the tip of this orifice, ultrasound is going to be already been vibrating. It is based on the piezoelectric effect. Once it start vibrating, it produces the droplet. It is going to be break down this droplet. These droplets are again into smaller size. Okay. So these are the finer droplets you can see over here compared to normal your spray. Okay. Or normal atomization, high pressure atomization. This is more finer droplets. Okay. You can also use other methodology that I will tell you later. See, this is how these are the droplets. Okay. What is been done? How capture the size of a droplet? Is it possible to capture the size of this droplet? How it is been done? You can see here. For example, that is an atomizer. Some of the part, for example, it is high shutter speed camera has been attached, like 6,000 frames per second, and micro lens has been attached, and then you can have catch this droplet size, and then you can count. It is called as a Sutter diameter. Okay. So it is interesting that you can grow these nano rods. Okay. With the technique you change, structure will change. Okay. So this is very much important to use this rods actually. Okay. So this is one interesting aspect. Okay. Now I will tell you the maybe other techniques are there released later. I think not useful. I will just close this with one commercial scale how it has reached. I will tell you about nano calcium carbonate, and then we will close the session. Okay. Nano size calcium carbonate. This is very much we have used it, and we commercially scaled also. My student is doing, he is already doctorate, and one is technology transfer, we did it in Ahmedabad. Okay. So these are the large scale production. Okay. Calcium carbonate. Where it is been used, maybe you are thinking it is used as a toothpaste or paper. They are very small applications. Major application is a composite. Which composite? PVC cable, PVC pipes. Okay. It contains as a filler. Okay. Almost 30%, 25 filler, percent of filler gives the ghost of a calcium carbonate. Okay. And nano size calcium carbonate has a very large demand in what it is called adhesive. Okay. PVC adhesive. So, but problem is that making it a large scale, in India the people are, maybe it's been done in the micro size particle, but scaling up in the nano size is very difficult because it requires a very specific shape. If you look, the shape is required was in a cubic shape. Okay. Cube shape for the whatever the PVC and other adhesives are required, as cubic shape is required. It is called as a calcite. Cost is very high, 200 rupees kg for example, nano size. commercially if you get even 150 rupees kgs also you get, and 10 rupees per kg also you get a calcium carbonate. But this is a specialty chemical additive. So it has been using it as a nano size filler, okay, in the adhesive. Specific adhesion is there. If you throw that adhesive, it should be attached to the surface, right? Thixotropy should be there. So such a kind of adhesives has been prepared using nano size. So how it has been done, I will just show you. When you go to the lab, you can see this methodology also, okay. It is a hydrodynamic cavitation based methodology. As I told you, ultrasound, you can make it using the hydrodynamic cavitation. You know that pumps usually been used, and the 40% of the energy has been lost because of a cavitation. Cavitation was nothing but what? When there is what is called, in the conduits are there, the liquid flows through the conduits, maybe for example orifice or venturi, there is a difference in the pressure, okay. So sudden collapse, sudden drop in the pressure will release the cavities or bubbles, okay. They collapse and that releases the energy, okay. That is a very instantaneous process, but it is very effective for the micro mixing as well as generating the radicals, okay. So commercially you can make it this process. So usually calcium hydroxide been added into CO2 gas. Commercially there is different process again, but to be produced into that particular things you can use it, and then you can produce this calcium carbonate, okay. So I will show you, this is somewhat smaller setup for 15 liters, okay, to be produced the slurry, and you can get this calcium carbonate. You can see here, industry doesn't require your calcium carbonate to be remain hydrophilic in nature. PVC pipes or PVC industry, it doesn't require the PVC, it should be complete hydrophobic. It should hit the water. If it is have the water moisture content, you will find the patches onto surface. You have seen any PVC or cable or this one with a patches? No, because it has this, made it with a calcium carbonate with a hydrophobic, okay. So you can see here, you can see that as a contact angle, okay. If you put the water drop onto the surface, it will spread, right. If the surface is hydrophobic, it will show the contact angle bigger, droplet, right. Contact will be almost 150, okay. You can see here, and you can see that calcium carbonate difference, okay. Size wise also very smaller. You can see here the how much size is 30 to 41, very narrow size. Almost all the particles are in the range of 30 to 50, let's say. So this is the nano size calcium carbonate. In this way you can have production as a polymer composite. It can be used in pharma industry also, in adhesives also. I will show you some of these nanocellulose also, one of my student has carried out. And that what I was telling about that calcium carbonate, he has first order, he also got it from one of the company, okay, for to produce this nano size calcium carbonate, okay. So it is on to the trial basis, but 500 kgs is good enough for initial start, right. So there are good opportunities to be have a continuous manufacturing. This is not a continuous manufacturing. This reactor is a process intensifying device, okay, whatever I have mentioned. Orifice and venturis, you put it and then you produced it, okay. So it is gives you the what is called semi-batch kind of thing, you can say, okay. So this is from my side. If you have any questions, okay, let me know, then I can explain you. If you want to come to my lab, you are always welcome. Regarding that platinum, I will show you how the fuel cell is been prepared. So these are the fuel cell components, okay. In that one MEA you can see here, inside there is a stack. This is a stack. In that one, MEM membrane will be there. Okay. In that one, platinum catalyst has been coated. Okay. So that is in the nano size. Okay. Some other performances are there for you. It's not much interesting. Okay. For you, for the nano size system. Okay. So if you don't have, you have any questions, let me know. Otherwise, you can shirish@nitw.ac.in. Okay. You can contact or you can come and see in the lab now. That will be, you can talk with my students. Okay. You can see what they are doing. If you need a nanocellulose, you can come work with them. You can want a calcium carbonate. Yeah.
Sir, can pressure and time can affect the morphology of this nanomaterials?
Yes. Yes. Specifically, time will affect. Pressure doesn't have the much impact, but time has the very impactful. Okay. Because with the pressure, basically your flow rate will change. So it has ultimately the impact on that one. Okay. That's what we did it lot of optimization for nanowires. Just changing the flow rate, just changing the concentration, time, temperature, and the capillary length also. It has the impact. So once it is finalized, then it will be easy. You will get that almost in the same size. Okay. Yeah, different kind of morphology. Yes, you can do it. It depends on the which material again you need to do it. Okay. For all you say that nickel nanowires I want, then again I have to see the precursors type, concentration, and then can. But for silver nanowires you can do it. Okay. You can have your own configurations. You can start working on that. Okay. So there is a, what is called, I forgot the name. Bharat Cement is one of the major cement industry in South India. His son is there, you know. He has started recently Bharat Semiconductor, I think. Okay. In that one, you people also have mechanical engineers have the opportunities. You can think about, you know, preparing this semiconductor, thermal insulating materials. Or this composite related to that, okay, for the batteries and you know, electrolyzers also. Electroplating cathodes and materials has again the new demand of material. You can think with that, okay. So your question was definitely it has to be, as see the atomization again has the different conditions. Residence time orifice change, surface tension also has the impact, density has the impact. So it will be going to change the based on this parameter. Okay, just orifice size. For example, say it is called as a capillary number, as well as you know, density, surface tension. They are majorly impacting. Okay. So hydrophobic nature will have also impact. Okay. So it will impact on the droplet size. It will impact on to particle size. Okay. Because reaction is also kind of what it is called, everything, there are phases are there. Growth is taking place, you know, death is happening, particle remain stable, they are agglomerate, they will come together. These all different mechanisms are been happening in the reaction. So the same thing in the micro-reactor also will have. Okay. So these are been impacted by the other parameters, right? Temperature, pressure, and velocity, flow rate, residence time. Okay. Okay, then you can go and see in the lab. Okay. I have one meeting. Okay. But I will join after that. There is also fuel cell and other things. You just go and look and see that one, and later you can have. Okay. Thank you very much. Okay. Thank you. Yeah, you have a question? Yeah.
Glues and microchannels that machine.
Glues and?
The grooves and microchannels.
Yeah, for the fuel cell you are talking, it has been done with a CNC machine, very specific. Okay. With a graphene CNC machine, we given the design. Mechanical engineering, you are that old batch student only, they did it. with my student, and it was done. These are from, we made it actually in Nasik, we given for the grooving for polar bipolar plates. Okay, you can do that grooving now. It's available. Okay, try to see that you people try to file the patents. You can have your own methodologies, technologies. Okay, make it. It's possible is there everything you can have. You know, if you want to have startup with this, our innovation center is there. We are going to fund also. Okay, so my student has got going to be got the funding. He has got this Ajanta Pharma. He got mint chocolate or mint some tablet is there. In the tablet they are adding that calcium carbonate to have better performances. So they want a nano size. So they got the order of 500 kgs. Okay. So manufacturing cost hardly whatever you use it doesn't go more than 10 rupees, 12 rupees per kg. Later he can increase the cost. You can understand. So one of the Florex is one company startup of my student. He gives the demonstration of that micro-reactor only. He has his own configuration. Pune it is there. You can go through it. Florex. You can go through the Google also. Florex is there. FLOWREX. Florex. Okay. One demonstration he charged 2 lakhs rupees. Just to demonstrate 1 hour, whatever in 1 day. Demonstration, 1 week, for whatever you have the chemistry, you do it for 1 week, whatever you want to use it in 1 week you do it. It takes charge 2 lakhs rupees. Okay, so you can imagine that in 12 months, even he remains empty for whole 6 months, still he will earn good money, right? Even in the half months he doesn't do anything. Even if you get 2 orders per month, okay, so 4 and 48 lakhs rupees, nothing much, right? Everything is costing, everything you let 20-30 lakhs rupees is easily you can earn, right? And he has very big, our seminar hall complex is there, like 2 floors in a big industry is there, okay, pass out in 2013 or 14 only. Today is 24, 25, I mean 10 years he established that. What is that? What? Process intensification and micro-reactor technology. Okay, all glass based, all FR based reactors. Okay, so you can think it, it's not like we people are making the differentiations that we are chemical, we are biotech, we are mechanical, we are metallurgy. Practically if you see, is all interdisciplinary requirements. Industry is not working. You solve my problem, whatever engineer is, you are not asking about that. Correct? So look into that and have a good,
Try to see that whether you are getting possibility to connect with him. Try to go in their lab, work with them 1 week. If you get an opportunity, even paying the money, you go.